Hi there. This video is for section 3.10. The two main objectives is to find the local linearization of a function and the associated differentials. Don't worry if those vocabulary words are not known. I will explain what they are. And also, we're going to be using those local linearizations or differentials to approximate the value of a function. All right, let's get started. The first thing is we need to start with some vocabulary. So we have this idea of local linearization. It comprises of two words, local and linearization or linear. So we need to make sure that we know what local and linear is. So local essentially means at a moment or at an instant, which means at a like exact place. Now, exact in calculus, of course, means we can be like 0.0001 away, the whole limiting idea. So local just means you're extremely close to a specific point. But we think of that in terms of a limit being, approaching infinitesimally close. And linear, well, linear, you know what that is? That's the whole y equals mx plus b thing. It's a constant rate of change. Now, I know we don't really use y equals mx plus b very much anymore. In fact, we're not going to be using it for this section either. We're going to be using the y minus y1 equals mx minus x1. Now, if you look in your book, the book will give the equation y equals y1 plus mx minus x1, or perhaps it will give you the equation y equals y1 plus f prime x naught x minus x1. Now, when I first learned this section many years ago, I memorized these new formulas saying, okay, if I do local linearization, I have to use one of these formulas. But I want to sort of tell you that these are the exact same formula as the y minus y1 equals mx minus x1. Let's look at the top one. You might see that these are identical just by moving the y1 to the right-hand side. If we add y1 and put it in front, normally we would put the plus y1 at the end. They put the plus y1 in the beginning. That's the exact same equation, but just solved for y, which is what we kind of did anyway, but just putting that y1 in the beginning and not at the end, the plus at the end. And then the second version of this, the only difference is we've replaced m by f prime x naught. But this makes sense because the slope of a line, slope of a tangent line, is the same as the derivative at a particular location, right? So the derivative measures slopes of tangent lines. So we have this f prime x naught just saying that, you know what, we're going to find that slope by using the derivative and plugging in a value that we're interested in. That's the instant value that we're interested in. So anyway, when you start looking at some of the book information, you'll start seeing perhaps these more complicated versions of the exact same y minus y1 equals mx minus x1 equation. You can use whatever you'd like. Just wanted to dispel the fact that it's yet another new formula to learn. All right, so let me show you how to find the local linearization and what it means. So first of all, I'm going to give you a visual of what we're going to be looking for. So I'm going to pop over to Desmos. I have an equation here. The function is 10 e to the 0.05t. It doesn't matter what equation it is. This is just a demo problem. And I have a particular point, which is at 12. And that's this point right here. And so that's my instant. My instant is 12, and the y value, when I plugged in 12, I got 18.22 something. So I just plugged that value 12 comma 18.22, right? So that's my point, my instant on my function. And the idea here is if I zoom in really close, that function looks like a line, right? In fact, this is the equation of the tangent line. Here's my y1 plus my slope. I found the slope by finding the derivative and plugging in the value. There's the derivative with the value plugged in right there. And then x minus, the x value 12, which is the point right here. So if I graph this little derivative, you can see that this dotted green line is really the exact same thing, or almost exactly the same thing as the black line. If I don't look at the close-in view, you can see that there's the tangent line at that particular point, and that's not the same as the curve. But locally, if I zoom in, there's no difference really, practically speaking, between the line and the function at this immediate location right here. So we're going to be using the local linearization to simplify a complicated function. So functions go all kinds of different directions. What we're going to be doing is we're going to be looking at them at a very microscopic viewpoint. So it looks just like a straight line. And then we're going to use all these little straight lines because we can look at that at any location. Any location we can look at, it's going to be a straight line no matter what we do. And so different straight lines at different locations, because they'll have different derivatives, etc. But we're going to put all that information back together later on and do all kinds of really interesting math things based on the fact that at a really close-in view, these functions look like straight lines. That's the local linearization. All right, so let's go back to the first example. It asks to find the local linearization of this random function at a point that I specified. So local linearization means the local line, the local linear thing, and we're just going to find the tangent line. So local linearization, to find the local linearization, you're just going to find the tangent line. And if you remember finding the tangent line, which you've done several times previously, then you know how to solve. How do we find the tangent line? Well, it's a line. To find any line, we need a slope and a point, and then we can plug it into our formula. Well, we know an x value, so we just plug that in to find the y value. So f of 2 would be the y value. And that would be 3 times the ln of 2 minus 1 plus 4. So the y value is 3 times ln of 1 plus 4. Ln of 1 is 0. So this is 3 times 0, y equals 3 times 0 plus 4. And that gives a value of 4. So we know the point is 2 comma 4. So that's half of what we need to find an equation of a tangent line is a point, 2 comma 4. The other thing is we need a slope, right? So how do we find the slope? Well, that's just the derivative. So I'm going to write the equation in y equals form just because I like that better than the fx notation. So here's my y equation. And then I'll just differentiate it and find the slope of the tangent line. So the derivative ln of, well, the 3 doesn't do anything. The derivative ln of stuff is 1 over stuff times the derivative of the stuff. That's our chain rule with the ln shortcut rule. Write the right symbols here, x minus 1. And then the derivative plus 4, well, the derivative of any constant added on is 0. So that's what it is right there. Dy dx is equal to, well, the derivative of x minus 1 is just 1. So this is going to be 3 over x minus 1. This whole part is just 1. And I'm just going to plug in a value to find a specific slope, not just all possible slopes at any value of x. I'm looking at the particular slope at x equals 2. Remember, that's the x value. That's our instant. That's our local place that we're looking for. So at the moment when x equals 2, I get 3 over 2 minus 1, which is 3. So I have a slope value of 3, and I have a point of 2 comma 4. And so I just plug that in, and that gives me my equation of my tangent line, which therefore is my local linearization. So I'm just going to go back to my y minus y1. The y value is 4 equals m x minus x1, which is 2. And then I'll move the 4 over. Again, you don't have to put it in the front. The math people do it for some reason. You could put it in the front. You could put it at the end. It doesn't really matter. This is my local linearization. We oftentimes don't use the letter y anymore so that people don't get it confused with the original equation. So oftentimes they call it like Lx just to emphasize that's the local linearization. It's the same thing as y equals. Just make sure you don't confuse it with the original function y value. So that's the local linearization. So that line basically looks identical to the original function at the instant when x equals 2. So anywhere right around 2, they are the same. All right, well, that motivates part B, which is to use the local linearization to approximate f of 2.5. Now, 2.5 isn't instant isn't like super close to 2. I mean, 2.00005 would be really close to 2. 2.5 is 0.5 away from 2. It's going to be an approximation, so it might be a bit off. It won't be exactly the same. However, we can approximate it, and later on we can actually kind of compute an error, how far we're off. But right now, we're just going to approximate something, and 2.5 is reasonably close to 2. So we're going to use it knowing that our answer is not going to be exactly correct. It's going to be a bit off because 2.5 is not infinitesimally close to 2. But the value of the function at 2.5 will be approximately the same. Let me make sure that looks like 2.5. The value of the function at 2.5 would be approximately the same as the value of the tangent line at 2.5, which we call L, right? So those are about the same because we're right around 2. Well, I know what the L function is. That's the function over here. So I would do 3 times the x value is 2.5 minus 2 plus 4. So that means the function value at 2.5 is approximately equal to, well, 2.5 minus 2 is just a 0.5. So this is 3 times 0.5 plus 4. This is 1.5 plus 4, which is 5.5. So the value of the function at 2.5 is close to 5.5. And the great thing is that we didn't have to plug in 2.5 into the original equation. If you have a calculator or a computer, plugging in 2.5 into this original equation is pretty darn easy. But you don't have to. If you have a local linearization, you can find a pretty good approximation just by plugging it into the tangent line. And for you computer science majors out there, you may realize that in terms of computing efficiency, if you are okay with an approximate answer because you're rounding things or whatever, the computing power of doing a linear calculation is way more efficient than doing something complicated like a natural log. So there are reasons why we would like to use this other than just an exercise in pretending we don't have a calculator. All right, so that is what a local linearization is, and that's how we use a local linearization to approximate a value of the function, as long as what we're trying to approximate is reasonably close to the local, the instant that we found the tangent line at. All right, so we're also learning differentials. So I'm going to be doing the same problem, but using a differential instead of using a local linearization. Turns out it's basically the same thing. All right, so first thing we need to define what a differential is to make sure. Differential is like a d something, like in dy dx, right, which is our notation for derivatives. It's our Leibniz notation for derivatives. Dy is a differential, and dx is a differential. It's just a d thing. It's like pretend we separate the dx and the dy into two separate things. We get the top differential and the bottom differential. Differential, if I could spell. All right, and the idea is it's a small nudge in that direction. So dy is a very small change in the y direction, and a dx is a very small change in the x direction. You know, if I had some equation or function or graph or something, zoop, whatever, and I'm at a particular point, then if I go a little bit in the x direction, that would be a dx or a delta x. And if I go a little bit in the y direction, that would be a dy. And if I do dy divided by dx, that's rise over run, which is slope, which is, a whole derivative thing. So they're just writing this dx and dy and calling them differentials. All right, so let us first find the differential, and then let's learn how to use it to approximate the exact same thing we did before. All right, so to find a differential, you're going to find the dy dx, which is the derivative, which we already did, but we can do it again. I mean, it's up here. I guess I'll just write it down instead of going through all the steps again. The derivative, is up here. So from before, that's not like the word from part A, we know that dy dx is equal to 3x minus 1. That was our derivative from before. And so we can find what the differential dy is just by getting rid of the dx. I have to multiply both sides by dx to eliminate it from the left-hand side. And that gives me the formula dy, the differential of y, is equal to 3 over x minus 1 times dx. So not much new going on here, but we're just solving for dy, right? We're just getting dy as a formula as opposed to getting dy dx as a formula. Just cleaning this up a little bit. All right, so that's the differential. Boom. When they ask for the differential, you just find the derivative and solve for dy. Or solve for dx. They don't usually want to find the dx differential, but you could, if they wanted to, find the dx differential just by solving for dx. Right? Same thing. All right, so now how do we use the differential to approximate the value? Well, the differential is a little nudge, right? So we start off with an xy value. So we have our starting value of xy. So our starting xy, well, remember from before, we found it, right? So the starting xy is 2 comma 4. So we're going to start off with 2 comma 4. And this is from part A. I mean, I could do it again, but it's the same. It's the exact same calculation. We still get 2 comma 4, right? So we have 2 comma 4. That's our starting location. We're going to be nudging this a little bit in the x direction. So we're going to be nudging it a little bit this way. That's our dx. Let me try a different color. We're going to be nudging it this way. That's our dx. And we're going to be nudging it this way. That's our dy. Right? So all we have to do is figure out what our dx nudge is, and we can calculate our dy nudge. Okay, so what is the dx nudge? Well, the dx is how much you're shifting in the x direction. So we started from 2 comma 4, and we nudged to 2.5 for the next value. This is x equals 2.5. So right here would be x equals 2.5. Oops, not 2 comma 5, 2.5. So how much did we go in the x direction? How much did we nudge in the x direction? We started from 2, the x value of 2. We went to 2.5 because that's our value that we're looking at. We went 0.5 plus 0.5 in the x direction. So that means our dx is equal to 2.5 minus 2, or 0.5. So our dx, our nudge in the x direction, is 0.5. How do we find dy? Well, we have a formula for dy. Right? Our formula for dy says that dy is equal to 3 over x minus 1 times dx. So we know what dx is. We also know what x is, right? So we get a dy value here, right? Our x value is 2. Our dx value is 0.5. So we have this x value of 2. We nudge it over 2.5. That gives us a dx value of 0.5. dy value is a formula. So I do 3 over 2 minus 1 times 0.5. This is 1.5 if you do the math there. So we know that we've nudged 1.5 in that direction. So if we started at 4 and we nudge up 1.5, then where do we end up with? Our y value was originally 4. Our dy value, this is our dy value, was 0.5. So we start at 4, we go up 1.5. So what y value do we end up at? If you're thinking 5.5, you are thinking the right answer, because 4 plus 1.5 is 5.5. So 5.5 is the y value, which is what we're seeking. We're trying to find the y value at 2.5. So if you nudge over this way and find the new x value 2.5, then you nudge up this way and find the new y value of 5.5. So y is approximately 5.5. It's not exactly equal to 5.5 because, of course, this thing is not a straight line. It's curving, but we should have a very good approximation of 5.5. And check this out. In our previous problem, we used the local linearization. We got an approximation of y is 5.5. And we used a differential, and we nudged it a little bit and nudged it a little bit. We got an approximation of 5. It's the same thing. It's the same darn thing. It's just kind of a different way of looking at it. Calculus, for whatever reason, teaches students to do it both ways. on an exam, you can usually pick, the version that you want, unless they specify, which is not often. We just want you to be able to approximate using either a differential or a local linearization. So that's the general idea. I'm going to do one more problem, but that's kind of the idea of this section 3.10 is understand how to create a local linearization, how to create a differential, and then how to use one of those, or both of them, in fact, to evaluate or to find an approximation for the value of a function at a nearby x value. All right, so last problem is over here. Let me zoom in a little bit. All right, so we have a problem here where we're doing a approximation, and we'll do it both ways using the differential and using the local linearization. So this E says use the local linearization to approximate the value of 1.02 to the 10th power. Now there's no equation here, so sometimes students get a little stuck of where to start. So we like nice numbers to plug in. 1.202 is not an easy number to raise to the 10th power. So that's what we're going to replace by x. So our function is going to be y equals x to the 10 instead of 1.02 to the 10. And if you're not sure what to do, just look for the messy number, right? So if there's some funny number there, whatever, 1.97, you're like, okay, 1.97, it's about 2. So I'll just round it to 2. Here, 1.02 is about 1, so I round it to 1. But that rounding is where the x is, because x is not exactly 1.02. 1 is not exactly 1.02, so I'm going to use x there, and I'm going to find the local linearization at x equals 1. Always choose a nice round number for your local linearization, an easily computable number. 1.02 is not so easy to compute with. 1 is very easy to compute with. And notice that 1 is very close to 1.02. So we have this function, something raised to the 10th, where that something we're looking for is 1.02, but we're going to use the function at x equals 1 to get the original function, the original derivative, and then use our local linearization to approximate it. All right, so hopefully that wasn't too confusing an explanation. I don't feel like I did the best job, but hopefully I could make up for it in the explanation of the local linearization. All right, so thing to the 10th is x to the 10th, and we're going to find the local linearization, which is the tangent line. So to find a tangent line, I need a point, and I need a slope. What's my point? Well, we're choosing x equals 1 because that's a very easily computed value, and it's very, very close to the thing we're looking for, which is 1.02. So we're trying to find 1.02. We use 1 as a nice value that's close by. We can find the value at 1 and use that to approximate the value at 1.02. So if x is 1, what is the y value? Well, you can plug it into this equation. The y value when x equals 1 is 1 to the 10th, which is 1. So our point is 1 comma 1. How do we find the slope? Well, that's just the derivative formula. So if we have y equals x to the 10, then we get dy dx is 10x to the 9th. Now, this is the derivative equation, which is all possible slopes of all possible tangent lines. We are not interested in all possible tangent lines. We're interested in one specific tangent line, which is where x equals 1, right? That's our big value right here. So we plug in 1. 10 times 1 to the 9th is equal to 10. So we know our slope is equal to 10. So once you have a point and once you have a slope, you can write the equation of the tangent line. Okay, so y minus y1 equals mx minus x1. You probably have a faster way of doing it. Use your faster way if you want to do it. I just use the same formula. To me, it's easier just using a single formula. The y value is 1. The slope value is 10. The x value is also 1. So that's our tangent line. I'll move the 1 over to the right-hand side. I'll put it in front. How about that? Instead of putting it at the end, which I normally do, I'll put it up in front just for people to see that it's the same thing in front. So that's my local linearization. I'm going to call this Lx so that it's not confused with the original y value or y function. So this right here is the way we would typically write our local linearization at x equals 1. So that's the localization of this function x to the 10th, right at that instant when x equals 1. So anything close would be good. So how do I use the local linearization to find the value of 1.02 to the 10th? Well, the value of the function at 1.02. So remember, our function here is y equals x to the 10th. So 1.02 to the 10th would be, that's the value of the function. So the value of the function when x equals 1.02, right? That's when I plug in 1.02. That's approximately the same as the value of the linearization at 1.02, right? So this is the whole point of linearization, that it's basically exactly the same as the value of the function locally, right? Right at that little location. So what is L of 1.02? Well, we know what our L equation is. It's right over here. So L of 1.02 is 1 plus 10 times the value 1.02 minus 1, which is 1 plus 1.02 minus 1 is 0.02. Oops, not 0.2, 0.02. When I multiply by 10, I get 0.2. I guess you can do this with a calculator faster, but I'm just writing it out because I'm too lazy to grab a calculator. This is 1 plus 0.2, which is 1.2. So the y value is approximately 1.2. So when you plug in this 1.02 into 1.02 to the 10th, you're going to get approximately 1.2. And you can use a calculator to check how close that approximation is. All right, so that's a localization to approximate the value that they're asking. And we can also use a differential. It's the same process. Once again, we're going to be using thing to the 10th, which is x to the 10th. We're going to be using an x value of 1 because that's very, very close to 1.02. We want things locally. We're going to find the differential, which is the same thing as the derivative. But you have to solve for dy. So that's our differential. Then all we have to see is how much we nudge in the x direction. That's called dx. How much we nudge in the y direction. That's dy. I usually do a visual to help explain it to people. So we're starting at the point where x equals 1 and y equals 1. We're nudging over to 1.02. So that means that the x, or the change in x, the differential in x, is 0.02, because from 1 to 1.02, you could just subtract, and you could find a differential of x. Now we're looking for the differential in y. Y started at 1, and it went up. How much did it go up? Well, we use this formula to find out how much it goes up. So dy is equal to 10 times x value to the 9th times the nudge in the x direction, which is, here it is, 0.02. So that's a 10. 1 to the 9th is just 1. 10 times 0.02, which means we're nudging in the vertical direction by 0.2. So we started at 1, and we nudged up 0.2. So you started at 1, a y value of 1, and you went up by 0.2. So where's our new y value? It's 1.02. So we get a y value of approximately not 1.02. Let's make sure I can do some arithmetic. So once again, I started at 1, right? And I went up 0.2. So 1 plus 0.2 is 1.2. Okay. So this y value up here is going to be 1.2. So that will be our approximation using a differential. So we know y is approximately 1.2, which is the same thing we did using the local linearization. We got the same approximation. Again, they're just different ways of doing the same thing. All right, so that's the idea of local linearization and on differentials. Hopefully you found this video helpful, and please reach out if you have any questions or any clarifications, any what-if scenarios. I'll be happy to help. All right, please enjoy your day.